introduce Mark. For those of you who don't know, Mark Uhran has been with NASA doing the space station for quite some time. He's been working on determining practical applications of orbital space station since 1984, which, as we talked about this morning, is really when this all began starting in the concept phase. And then he's had a number of key management positions, both private and public sectors. Currently, he's the Assistant Associate Administrator for the International Space Station at NASA headquarters, where he's responsible for program-wide cost, schedule, and performance oversight. He also leads NASA's effort to operate the space station as a U.S. national laboratory in the post-assembly phase. Mr. Uhran holds a BS from Columbia Cornell University, a master's from the University of Maryland, and an MPA, Master's of Public Administration, from Harvard University. He's also an Associate Fellow of the American Institute of Aeronautics and Astronautics. Please welcome Mark Uhran.
Thank you, Frank, and thank you to the American Astronautical Society for the award presentation to Bill Gerstenmaier over lunch. He's taken this program a long way in the past several years, along with the entire International Space Station team, and it's always gratifying to see some recognition for the efforts of leaders like him. Everybody's attention is turning to the International Space Station Utilization Program now that the assembly is drawing to a close. Bill talked this morning about the tremendous capacity and capability that's inherent in the platform. And I'm proud to say that we set many of those performance requirements back in 1993 at the Critical Design Review, and we met every single performance requirement: crew time, power, thermal, data processing, so that the facility is ready. What I want to talk to today is not so much about the capacity that we have, since I think between the several discussions this morning in the panels, you'll agree that it's an extraordinary capacity, but the potential for discovery. And what I'll do is I'll spend a lot of the time talking about what has already been discovered and the significance of it, because many of the discoveries are already on the table. And the real question is not, what are you going to discover for me next, but why are these discoveries not going the next step? And we'll talk about that specifically. But before I do, I should round out with, this is really about positioning the space station for the next decade. What can we as an agency do to make sure that we have lowered the boundaries as much as possible and created the most accommodating environment possible to enable this R&D to proceed, and to enable it to proceed not quickly, but certainly before the end of the decade, because as several people noted, we only have 10 years, possibly a few more, but we're basically designing for a 10-year opportunity here, and it's highly unlikely that there'll be a second International Space Station funded by the government. So we have to demonstrate with this iteration that there is a comparative advantage to this environment, so that by the end of this decade, we can hand that off to the next generation to take advantage of that environment. So I'll give you specific examples for that as we go along. There's really two areas that have to be looked at before we start getting into the view graphs. One is, what are the R&D prospects? Are there really prospects here that can have significant impacts on the ground in our daily lives, creating new industries in the future? To many people, there are no prospects, and they've already dismissed it. Those are the naysayers. To the visionaries, the prospects have already been demonstrated, and those are what I want to share with you here today. But then there's a second and perhaps even more important part of the problem, and that is, if you assume that the prospects are indeed there are competitive advantages, they have been demonstrated, and they will make their way into translational applications in the future, there's still programmatic aspects that have to be overcome in order to realize the potential of the space station. So although I'll spend most of my time giving you examples of why there's no question remaining in my mind that the R&D prospects are there, but the programmatic prospects are the challenges that lay in front of us, and we'll close with a little discussion of those. To kind of put this in context, you can look back over NASA's history And in the first 25 years, across the Mercury, Apollo programs, the Skylab program, we were really just learning to live and work in space productively before we even began the research. In the last 25 years, basically with the dawning of the space shuttle program, we began to move into the experimental laboratory phase. Granted, we did some research on Skylab, there was even research done on Apollo, but we didn't really move into the lab phase until the shuttle allowed us 5 to 7 mission duration days and multiple missions every 1 or 2 years. Well, if we look back collectively over the past 25 years at the number of space labs, space hab, the shuttle mirror mission opportunities, and then the station assembly opportunities, you find that there's roughly about 1 year of cumulative time available in the laboratory environment. 1 year is not a lot to work with, but what I would do is I would characterize that last 25 years as the survey phase. During that survey phase, we were basically pursuing unfettered research into biology, chemistry, physics. It was unconstrained. And as a result, there were a lot of provocative findings. There was not a lot of opportunity for repeatability. Not a lot of opportunity to carry those experiments from 1s and 2s to 10s and 20s in order to really move it from one end of that research spectrum, basic research, down to the opposite end of that spectrum, applications research. And of course, that was one of the driving reasons we decided to build a space station, was to be able to advance that research. That's the opportunity that's ahead of us today. The other thing that we should point out is you don't make a discovery with a single experiment that turns into an application on the marketplace quickly. That's not within the experience of history. It can be 10 or 20 years before a given finding translates itself into the applications phase. And I'm going to give you specific examples of that as well. This is well noted by studies done by the National Science Foundation back in the 1960s, the TRACES studies. These studies were repeated by other laboratories. Principally, the Columbus laboratories did TRACES 2 and TRACES 3. And if you look back at those old historic studies on, what is the nature of the timeline from basic discovery to application, it is in the 15 to 20 year range. So I get calls all the time, what have you discovered yesterday? Or what have you discovered on the space station while you were building the facility? Well, nobody asked the Large Hadron Collider what were the discoveries that were made while you were building the Large Hadron Collider, but nonetheless, that's the business we're in. And we can still point to findings that are going to carry us into the future years of the station. Let's go ahead to the first slide. What I'm going to do is I'm going to step through 5 specific examples. We're going to start out looking at thermophysical properties measurement. Thermophysical properties measurement in space was long hypothesized as an advantage of the space environment because it gave you the opportunity to improve materials that were later going to be produced underground. So we began running experiments in the 1990s working with a research team at Caltech on using electromagnetic levitators. Some of you in the audience will be familiar with this, many of you will not. What the electromagnetic levitator does is it allows you to position a sample in free space, heat that sample through phase transitions, and resolidify that sample. Now, if that sample is an extremely complex alloy, where the thermophysical properties cannot be determined on the ground because the alloy suffers from contamination inside of a container, it allows you to identify those properties in orbit where you no longer are surrounded by a container. When you're in a container, you get nucleation at the container walls, and it confounds the observations. What this allowed the PI team to do was advance their understanding of how to form bulk metallic glasses. Now, what are metallic glasses? They don't have anything to do with window panes. Metallic glass is the difference between an amorphous molecular structure and a highly ordered crystalline structure. And so that's what this illustrates for you. The picture on the left, you'll see a very clear linear alignment. These are scanning electron microscope photos done by Huffnagel at Johns Hopkins, just to illustrate the difference between crystalline structure and then amorphous structure, which is a totally randomized structure. The reason people are interested in the amorphous structures is because their material properties can have higher performance. And this is exactly what the Caltech PIs were pursuing when they began doing electromagnetic experiments, levitator experiments in space. They were working on zirconium alloys in this case, they were zirconium-based alloys, and you can see here that the thermophysical properties information they gained through MSL experiments on the shuttle in 1997 were what allowed them to advance to being able to produce this liquid metal alloy. And let's look at just the yield strength of this alloy is double that of stainless steel. The elasticity, double that of stainless steel, actually more than double. Now, some people in the material science community believe that these liquid metal alloys could actually be the third generation of the materials revolution, a revolution that began with steel, was followed by plastics, and could lead to liquid metal alloys in the future. This was 13 years ago that the experiments were performed. 2 months ago, Apple Computer purchased the worldwide exclusive marketing rights for this material in consumer electronics devices. Not everybody in the program is aware of these kinds of advances, but they're very significant advances, particularly if put in the context of a potential third revolution in materials. And the reason it's a revolution is because these metallic glasses can be formed like thermoplastics into very complex structures with very high tensile strength and very high elasticity. And in fact, we're using some of these materials in our Mars Observer program today. And we're planning to continue this research with the Caltech group in the future. Let's turn to another example.